You should know the basic trigonometrical ratios, and if we first of all put in the names of the sides of a right-angled triangle, the longest side is the hypotenuse, and then the side which is opposite the angle, and the angle would be this angle here, is called the opposite, and the other length, which is next to the angle, which I'll move that away, is called the adjacent. And then we've got our trig ratios, or trigonometrical ratios, sine, cos and tan. So sine is your opposite divided by the hypotenuse, and your cos is the adjacent divided by the hypotenuse, and tan is the opposite over the adjacent. Quite a useful relationship is if we've got a right-angled triangle with the hypotenuse of length 1. And we know that the sine is the opposite. So sine is the opposite divided by the hypotenuse, and the hypotenuse is 1. So sine of the angle, theta, must be equal to the opposite. So this would be sine theta, if this angle here is theta. And similarly, you've got your cos of theta is equal to the adjacent divided by the hypotenuse, which is 1. So again, the adjacent length must be equal to the cos of the angle. And we know that tan is equal to the opposite divided by the adjacent. So we've got another relationship for tan, which must be sine divided by cos of theta. So tan theta is sine theta over cos theta. Another useful way of seeing sine and cos is looking at it as a circle. And let's say it's a unit circle, so the radius is 1. And I've got an angle here which I'll call theta. And let's say all the other triangles are congruent. I'll write that word, so congruent. And congruent means that they're exactly the same. So the lengths are the same and the angles are the same. So I'll put in the angles there. Now, I'll label the points A, B, C and D. So the coordinates for A is the x-coordinate must be the adjacent, which, because the hypotenuse is 1, that must be cos theta. The y value, which is this one here, is the opposite, which must be sine theta. And B, as the x-coordinate is negative, we've got negative cos theta, and the y value is positive, so that's sine theta. So all these lengths are exactly the same because the triangle is congruent. C, the x and the y are negative, so that's minus cos theta minus sine theta. And then D is the x-coordinate this time is positive, so cos theta. The y value is negative, so that would be minus sine theta. So let's have a look at that again, and we're going to think about, are they positive or negative to start with. So in the first one, which was point A, we've got your x-coordinate and your y-coordinate are both positive, so sine is positive, cos is positive, and because tan is sine divided by cos, positive divided by positive is also positive. In coordinate B, you've got your sine, which is the y-coordinate, is positive, cos, which is the x-coordinate, which is negative, and tan is sine over cos, so that must also be negative. The third quadrant, which is coordinate C, both the sine and the cos are negative, and tan is negative divided by negative, which is positive. And tangent could also be thought of as a gradient. And if we look at this line here, it's got a positive gradient. Sine for coordinate D is the y coordinate, so sine is negative. Cos, which is the x coordinate, is positive. Sine divided by cos is negative. And again, we could have think of that as being the gradient of this line, which is a negative gradient. Now let's think of some other values which would give us exactly the same as cos theta. Or sine theta, rather. Now the first one would be the y coordinate for A. Another one would be the y coordinate for B. And they're exactly the same. So that would be sine of theta, or sine of the whole semicircle minus theta. So we're looking at this angle here, which is 180, or let's call it pi, minus theta. That gives us exactly the same. Now another value would be this one here, but it's actually negative. So that's equal to, that's equal to minus sine. And what's that angle there? Well, it's 180 plus theta, or pi plus theta. And another one would be this one here, which again is negative. So I'll write that in as negative, so it equals minus sine, this time it's 2 pi, or 360, minus theta. And those would be the 4 different values that give us the same sine value. 2 of them are positive and 2 of them are negative. Now let's think about cos theta. Now cos theta is the x-coordinate, so we're thinking about here and here. And we can see that the x-coordinate for A and D is exactly the same, and it's positive. And the x-coordinate for B and C is exactly the same, and it's negative. So let's write that down. So we've got cos theta must be equal to the coordinate for D, which is cos of 2 pi minus theta. And that's the same as minus cos of pi minus theta. And for coordinate C, again it's negative, and that's cos of pi plus theta. So we've got the relationship between the 4 angles. Now let's think about tan theta. And with tan theta, we've got the gradient at A and the gradient at C are exactly the same, because they're both positive. And then we've got the gradient at B and the gradient at D, which will both be the same. So let's write that down. So tan theta must be equal to tan of pi, or 180, plus theta. So pi plus theta. And then the negative of that would be for B and D. So that must be minus tan of pi minus theta. And again minus, which is tan of, for D, that would be 2 pi minus theta. So we've got the relationship between the 4 angles. We've got some special results here. So let's start off with this triangle here. And let's say we've got 2 lengths of 1. which means the angle, or both angles, would be pi over 4 or 45 degrees. I'll write pi over 4. And using Pythagoras, the hypotenuse would be root 2. So let's have a look at sine, cos and tan. So sine, let's say, of this angle here is the opposite divided by the hypotenuse, which is 1 over root 2. Now 1 over root 2 is sometimes written as root 2 over 2, but it depends what we want to do with it. So I'll leave it as 1 over root 2. Now let's look at cos of that angle. Now cos of that angle would be the adjacent divided by the hypotenuse. And that's 1 over root 2 again. And then tan is the opposite divided by the adjacent. So that's 1 divided by 1, which is 1. Now let's look at this triangle here. Now this one is an equilateral triangle. And let's say each length is 2, 2. So this one will be 1 and 1. So let's just look at half of that triangle. So this angle would be pi over 3 or 60 degrees. Put that in there. And this angle here would be pi over 6 or 30 degrees. So let's look at 60 to start with. Or before we do that, let's have a look at the length of the opposite to pi over 3. So this length here would be 2 squared minus 1 squared, which gives us root 3. So I'll just put an arrow there. So that length is root 3. Now looking at pi over 3 and sine, or sine 60, so that's the opposite, which is root 3, divided by the hypotenuse, which is 2. So that's root 3 over 2. The cos is the adjacent, which is 1 divided by 2. And tan is the opposite over the adjacent, which is root 3 over 1. So that's just root 3. Now looking at the opposite angle, which is the angle pi over 6 or 30, and it's going to be the other way round. So sine 30 is the opposite over the hypotenuse, which is 1 over 2. Cos is the adjacent divided by the hypotenuse, which is root 3 over 2. And tan is the opposite over the adjacent, which is 1 over root 3. And 1 over root 3 can also be written as root 3 over 3. But again, it depends on what we want to do with it. Now, let's look at question 2. And the first question, I'm going to leave that one, and we'll talk about that one later. So we're going to look at the particular examples, which is tan of 15 pi over 8. I know that 15 pi, or rather, I'll write that again. So 15 pi over 8 is equal to 16 pi over 8 minus 1 pi over 8, which is 2 pi minus pi over 8. And we're going to use that relationship to help us. So tan of 15 pi over 8 must be equal to tan of 2 pi minus pi over 8. And the relationship there must be similar to tan of pi over 8. Now let's see if it's positive or negative. Now looking at our circle here, tan of pi over 8, which is over here, must be positive. And tan of 15 pi over 8, which must be in the fourth quadrant, is negative. So therefore, tan of 15 pi over 8 is minus tan pi over 8. Now let's have a look at the next example, which is cos 260. And let's do that in a different colour. So 260 must be somewhere around here in the third quadrant. And that means that the cos value is negative because it's the x coordinate. And we know that 260 is equal to 180 plus 80. So let's write that down. So cos 260 must be equal to cos of 180 minus or plus 80, and there must be a relationship with cos 80. So I'll just write cos 80, and let's have a look at where they are. So we know that the cos of 260 is minus, cos 80 is in this quadrant here, and it must be plus, so therefore cos 260 must be equal to minus cos 80. Now let's think about sketching sine, cos and tan. Now you maybe know what they look like, but it's always a good idea to think about what the critical points are for each one. So let's think about sine first of all. Now what about sine 0? You can do that on your calculator, but sine 0 is equal to 0. Sine 90, or pi over 2, is equal to 1. Sine 180, or pi, is equal to 0. Sine 270, or 3 pi over 2, is equal to minus 1. And then sine 2 pi is equal to 0. So I'll just do a quick sketch of that over here. So I'm going to split my x-axis into 4 sections. So the first one is pi over 2, and then pi, 3 pi over 2, and then 2 pi. And then I'm just going to plot those points. So I know at 0, it equals 0. At 1, or at pi over 2 rather, it equals to 1. And then at pi, it equals to 0. 3 pi over 2, it's minus 1. And then at 2 pi, it's 0. So we know that it must look something like that, a very rough sketch there. Now let's have a look at that on the graph. So I'm going to type in y equals sine x. Okay, now that's not a particularly good scale, so I'm going to make a slightly better scale there. And if I just zoom in sideways, there we've got a sine curve, or a wave, we could call it. It starts at 0, and just having a look at some of the features there. If we think about the 0 point, on the positive side it goes up and then down. On the negative side it goes down and then up. And we might think about kind of this as a pivot point at the centre, and if we looked at the positive side and rotated that 180 degrees, it would then sit on the negative side. So it's got rotational symmetry. Now let's do the same thing for cos. Now cos of 0 is 1, cos of pi over 2 is 0, cos of pi is minus 1, cos of 3 pi over 2 is 0, and cos of 2 pi is 1. So a very rough sketch. Again, I'm going to cut it into the 4 sections, and we've got 1, 0, minus 1, 0, and 1, and very roughly I'm going to draw that curve. So let's go and have a look on the graph what it looks like. I'm going to just change this curve here to cos instead of sine, And let's see what happens. Well, actually, we can see it's just shifted along to the left. So it's gone from here, just moved 90 degrees or pi over 2 to the left. Now this time, some of the features is if we draw a line along the y-axis, we can see that the positive side is a reflection of the negative side. So it's symmetrical about the y-axis. And that also means that for every value of theta, if we look at the negative value of theta, it's going to give us exactly the same cos value. And that will be useful later. Now let's think about tan. Tan of 0 is 0, and tan of pi over 2 is cos divided by sine. Now the sine value at pi over 2 is 1 and the cos value is 0, so when we go 1 divided by 0 we can't do it, so there's no value of tan at that point. Tan of pi is 0 and tan of 3 pi over 2, now tan of 3 pi over 2, we've got cos is 0, sine is minus 1. Again, we're dividing by 0, so there's no tan value at 3 pi over 2. And then at 2 pi, tan is 0. So a very rough sketch. We know that at 0, tan is 0. At pi, tan is 0. And at 2 pi, tan is 0. Now let's have a think about what happens when there's no tan value. Well, if the value doesn't exist, what we've got is an asymptote. So at those values, at pi over 2, I'm going to do a dotted line for an asymptote, and at 3 pi over 2, I'm going to do a dotted line for an asymptote. Another useful thing to think about is between 0 and pi over 2, is it positive or negative? Well, tan is positive. Between pi over 2 and pi, tan is negative. Between pi and 3 pi over 2, tan is positive. And then in the next quadrant, it's negative, because tan always goes positive, negative, positive, negative. Now, what's going to happen? We know it starts at 0, and it's got to be positive, so it must go up. The next quadrant, it's got to be negative, and it's got to finish at 0, so it must come up like this. Next quadrant's positive, so it must go up. Next quadrant's negative, so again it must come from negative to positive. So it looks like this. Now let's have a look on the graph. Now the graph software doesn't actually do asymptotes, so we can't see any asymptotes there, but we do know that there is an asymptote at pi over 2. I'll do that in a different colour so it's easier to see. So perhaps yellow isn't very good, but we can see the asymptotes there. And at minus pi over 2 and at minus 3 pi over 2. Now, having a look at the features of this graph, the sections of the graph all repeat, and between minus pi over 2 and pi would be one cycle or one period. So I'll write that word down, a period. And it goes between, well, if I have a look from here to here, that would be the next, where it's the next repetition, and that's an interval of pi. So we say the period is equal to pi radians, or 180 degrees. And it repeats at each pi. And thinking about the symmetry, is it a reflection symmetry? Is it a reflection in the y-axis? Well, we can see clearly it isn't. But is it rotational symmetry? And we can see that if the 0, 0 point is our pivot point and we rotate it 180 degrees, we can see that it sits on itself. So it is symmetrical but rotational symmetry. And just as a summary here, we can think about the period, the symmetry, and the range of the y values. So the period for tan, which we just mentioned, is pi, because it repeats itself every pi units. Now the sine curve is a cycle like this, and that goes from 0 to 2 pi. So the cycle, or the period, must be 2 pi. And similarly with cos, that starts high, goes down, and finishes high, and that's a cycle or a period of 2 pi. Let's rub those ones out. And let's think about the symmetry. And we've said that sine is not reflective symmetry, but it is rotational symmetry. But here we've written down symmetry about the y-axis. It isn't symmetrical about the y-axis. Cos, on the other hand, is symmetrical about the y-axis. And tan looks like this and is not symmetrical about the y-axis. Now what about the range of values of y? Now the highest point for sine is 1, and the lowest point for sine is -1, so it goes between 1 and -1. And cos is exactly the same, so from 1 to -1. Tan, on the other hand, goes up to positive infinity, and it goes down to negative infinity. So this is all the real numbers for the range of values of y. Now another fact about sine and cos, to do with the symmetry. Now sine of minus x I'll make that graph a little bit bigger, and the cos one as well. Now sine of minus x, so let's say we pick a value for x, and that's over here, so I'll call that x, and then we do exactly the same distance on the negative side, and that will be minus x. Well, we can see that you get the same sine value, but it's minus. So sine of minus x is equal to minus sine x. And if that's true, it would be a rotational symmetry of 180 degrees, and we say that it's an odd function. So I'll write that down. Cos, on the other hand, if we pick a value of x and then we take the minus x on the other side, we can see that the cos value is exactly the same. So cos of minus x is equal to cos of positive x. And if this is true, we say it's an even function. Now, I've got two congruent triangles here, and I'm going to put the first one into the circle, and the second one, I'm just going to rotate it 90 degrees, or rotate it the other way around, and put that into the circle as well. Now I'm going to label the angles, so let's say this one here is theta, so this one here would also be theta. The other angle at the other end would be pi minus theta. So this one here is pi minus theta, because it's a right-angled triangle. Now let's have a look at the relationship between the sine and the cos here. So having a look at theta first of all, and the first triangle here, the cos value, so let's assume it's a radius of 1. So the cos value for theta, so cos of theta, must be the same as this value here. And this value here, because it's a unit circle, is sine of the other angle, which is pi minus theta. So we've got a relationship there. Cos theta is equal to pi minus theta. And if we think about sine of the angle, or sine of theta, sine of theta would be this vertical part here, and we can see, looking at the other triangle, it's equal to this length here, which is cos of the other angle. So that must be equal to cos of pi minus theta. And this is a useful relationship which we'll see later on. Now we've come to the end of the notes now, and this is where you're going to try some examples yourself, just to check that you've understood the Chapter 8 trigonometry in C2. So the first thing I'd like you to do for homework, question 1, is to sketch the curve y equals 3 sine 2x plus 30. Now this is using the idea of transformations of graphs, which we looked at in C1, chapter 5. So just kind of recapping on that, the 3 would have the effect of stretching the curve in the y direction. The 2x would have the effect of squashing it in by a factor of 2, and the plus 30 has the effect of shifting it 30 degrees to the left. So have a go at sketching that curve. Now one thing to watch here is the fact that your squash is along the x-axis and your shift is also along the x-axis. So have a think about this question here. Find the coordinates of the first 2 positive intersections with the x-axis, and that might help you decide, do we do a shift first or do we do a squash first? The second question I'd like you to have a look at is this one here. So given f of x is the function is the function a sine x plus a number k, where k is an acute angle. An acute angle means that it's less than 90 and greater than 0. And the angle's got to be in radians, so I'll perhaps change that to pi over 2 rather than 90. You're going to find the coordinates A, B, C and D, and the values of A and K. Now you need to know where the points B, C and D are. I've just labelled those incorrectly, so let's just change those. Let's rub those out. Now the B, C and D are the intersections with the axes. So let's say B is the intersection with the y-axis, and C and D are the first 2 intersections with the x-axis. The last question I'd like you to look at is this one here. It's y is 3 cos ax plus b, and you're given that point A, which is the first intersection with the x-axis, is 100, 0. B, which is the second intersection, is 220, 0. So you might want to think about the gap and in terms of the period of the curve, and that might help you to think about what's inside the bracket here. And then D and E are the two maximum points. C is given and it's 0, a half. And I'd like you to find A and B. B you're given, and then C you're given, and I'd like you to find D and E. So you've got A, little b, D and E. So that's your last question for homework. So 3 questions for homework. And can you hand those in next week?